In this video, we'll take a look at Chapter 9 from Hanley, Shogren, and White's textbook, Introduction to Environmental Economics. The topic of this chapter is the economics of non-renewable resources. Let's look at this. So first, we'll talk about the classic hoteling rule. Then we'll look some at various ways we might try to measure resource scarcity. As a hint, none of these ways of measuring resource scarcity is entirely satisfactory. And then finally, we'll look a little bit at oil as being a case study. Right, so let's start with the hoteling rule. Right, so the basic claim of the hoteling rule is that the price of a non-renewable resource will increase over time with a growth rate equal to the discount rate. Right, so just to give you some kind of a sketch of the proof. Right. The first assumption we're going to make is that the discount rate is equal to the interest rate. I would say this isn't really a particularly dangerous assumption. Right? It's really kind of capturing a reasonable alternative when I'm thinking about moving wealth from right now into the future. Right? That gives me some sense of how I should discount the future. Right? I should discount the future when I'm thinking about the present. And a natural way of thinking of this is the interest rate you could earn if I took wealth that I have now and then just save it for the future. Right? So using the interest rate as a discount rate, it isn't particularly dangerous, and I think it's actually fairly standard. There's not much controversy around this, except that there are times that the interest rate, perhaps because of monetary policy, might not connect exactly with the discount rate, or the interest rate sometimes includes more of a risk premium than the discount rate would. But those are really the only kind of two exceptions we'll worry about, but we'll just make this assumption the two would be equal. Right. A second assumption is that there's some kind of fixed price in the second period. We're just going to think about a two-period model. This is really just to kind of fix our expectations and help us get the logic straight. You could very easily loosen this assumption of a fixed price in the second period. Right? And then what we really need to think about is considering the choice of whether we should sell the resource now, right, or hold it into the future. Right, so let's consider the first case. Right, so let's suppose that price in the second period, right, is greater than the price in the first period by more than the amount of the interest rate. So if the interest rate is, say, 10%, then we're looking at a case here where the price in the second period is more than 10% higher than the price in the first period. And perhaps it's 20% higher. Well, in that case, we wouldn't want to sell any of the resource. In fact, we'd want to buy up as much as we could of the resource, right? So certainly any we have, we're going to withhold, right, from the economy. We'll just hold on to it, right? Wait, we'll earn effectively in this case, say a 20% return instead of 10% we could earn from interest, right? So we'll earn that 20% return just from holding on to that resource. But since we're not the only ones that face this choice and this incentive, we would expect that lots of other firms who also have this good available to them would also withhold the resource from the market. Right? So as we're all withholding the resource, that's going to drive the price of the good up in this first period. So what happens then is that the difference between that expected price in the future and the price right now is going to shrink, right, as we're holding on to the resource now, which would drive up the price right now. A second case would be, well, let's suppose that the price in the second period is greater than the price from the first period, but by less than the interest rate. Now, it might also be that the price in the second period we expect to be lower than the price in the first period. That would also fit under this case. Okay. Well, if that's the case, then what we should do is take the resource we have right now, right, sell it all. Right? There's no point in carrying it into the next period. Right? We'll just sell it all, right, and then just invest in whatever interest-bearing investments we would have, and then we can just buy the resource back, right, in the future. Right? So just as a simple example, if I expect the price of, let's just say oil, so a bunch of barrels of oil that I could use, I could sell now, right, or I could hold to the next period. If I expect the price of oil to go up by 5%, meanwhile, say interest rates are 10%. In that case, it makes perfect sense for me to take all of my oil, right, sell it off, right, earn 10% on the money that I make, right, and then go back out and buy up that oil in the future, right? And yeah, I have to pay 5% more than what I got for when I sold it, but remember, I made that 10% in interest in the meantime, and so the interest is more than going to pay for the difference in price. Right, so, and I'm not the only one that has this incentive to sell it all. right? So there's going to be this rush from everybody that's holding on to oil in this case to rush out and sell it. Right? Well, when we all try to do that, that's going to lower the price right now. And by lowering the price right now, we'll have a greater difference between the current price, P1, and the price in the future, P2. Right, so case 1 showed us if that difference between P1 and P2 is greater than the interest rate, then it's going to tend to shrink. What case 2 shows us is that if the price difference is less than the interest rate, it's going to tend to grow. Kind of where we're heading. Right? So now let's suppose that the price next period is greater than the price in the current period, but by the amount of the interest rate. Right? So if we have a 10% interest rate, we also think that there's going to be a 10% increase in price. In that case, right, neither selling nor hoarding is obviously better than the other. Right? After all, I could just hold on to the oil that I have, right, and it's going to give me a 10% return. Right? Or I could sell some of it and take that money and put it into bonds or whatever is paying the 10% interest, and then I would have earned 10% that way. Right? So it doesn't really make any difference whether I sell or whether I hoard. Right? So the end result we're going to get is that some of the oil is going to be sold, right? Some of it's going to be held, right? And there's no obvious reason then why that price should necessarily change, because there's no rush, right, to either sell, right, or to hoard. Right, so I think this then kind of gives the logic of the hoteling rule, so why it is that the interest rate or the discount rate, right, is really the key in explaining how much prices are going to increase over time for these resources. And really it all relies on that ability to either sell them right now or wait and sell them in the future. Now, there is a graph in this chapter, so if you have the book available, there's figure 9.1. I find that figure very confusing. The way that it's set up, it has these 4 quadrants that are trying to explain price and quantity and time all at the same time. It was not obvious to me how these all fit together. I could kind of tease it out with some thought. So I'm not going to focus too much on that figure. Rather, let's look at this a little bit differently, a way that I think is probably so let's go ahead and look at a basic model instead of the kind of complicated 4-quadrant diagram. Right, so the first thing, we're going to have a total stock of 500, and really the choice for our producer is going to be when the producer sells those 500 units. Price is going to follow the hoteling rule over time. Right, so once we've established what the initial price is, then it's going to increase by the rate of discount, which will make the rate of discount 10%, which you can see here under number 5. I will also assume a linear demand curve where our quantity demanded is equal to 50 minus the price. So at higher prices, the quantity demanded will be less. Now, one thing, when you look at this, this does imply that if the price is at 50, then exactly none will be demanded. Right, so everyone is going to switch to some kind of alternative at a price equal to 50. The name we give to that price of $50, right, where the quantity demanded falls to 0, is the backstop price. Effectively, what this means is that it doesn't matter how scarce this resource gets, the price can never go over 50, or people will just entirely stop buying it. Instead, they'll switch to another alternative. And that is one thing to point out, is that how high that backstop price is depends on the availability and also the cost involved with switching to an alternative. And so if this happens to be a resource where we already have fairly available, not outrageously expensive alternatives, then the backstop price is going to be fairly low. On the other hand, if this is a good that is very unique in what it can do for us, and we don't really have very many good alternatives available, or they're very expensive, that would make the backstop price perhaps extremely high. Right? But in this case, we'll just go with a backstop price of 50. After all, this is just a demonstration. This isn't supposed to be about any particular market. Right? We're going to give just for the sake of making the math easy, we're going to have up to 50 periods that will allow them to use up the stock. So they have to decide how to divide up those 500 units between those 50 periods based on how the price is moving and the amount of demand they expect to see. And again, the rate of discount will make 10%. And so once we have all of these assumptions in place, really the only thing we have to do is figure out what the starting price is going to be that is going to use up this this quantity of 500, right, while following the linear demand curve in each period. Right, so I used Excel, right, to go ahead and solve for that initial price that would use up the stock. So this is it's actually a fairly easy tool to use. They call it goal seek. Right, so I just set up, here are the prices. The prices I calculated according to the hoteling rule. So the first one would be blank, right? The remainder calculated by the hoteling rule. I have the quantities, right? The quantities were determined based on the demand curve, and then I added up all of those quantities to make sure they're equal to 500. And you can actually tell Excel, right, pick that first price so that these quantities all equal to 500, and this is what we end up with. Right, so the blue line here would indicate the price, which you can see is increasing by 10% in each period. The initial price is right around $8.50, right? And then you can also see, right, the quantity that's demanded in each period. So you can see very clearly how the stock is being used up, and we're using it up fairly quickly at first. Right, so in that first period, we're using over 40 units out of the 500, right, and gradually decreasing that. The decrease here is because of the increase in price. Right? And that's also showing that the decrease in quantity is going to be accelerating over time as we run closer to running out of the good, right? Then we are using less of it, and using less of it in a sense faster, if that makes sense. Right? And that's really just because of the way the price path goes. The prices are moving up at the same rate, but at a faster dollar amount, and that is leading the quantity to decrease significantly. And you can see here we'll totally run out of the good in 19 periods following this optimal rule. And that's also the point where you can see we would just barely hit the backstop price of 50. Now here we can get some sense of how the rate of discount affects the time it takes to exhaust a resource. Right? So in this particular example, if I change the discount rate from 10% to 20%, that means that the price is going to be rising faster. It also means that the initial price will be somewhat lower. Right, but still, when all of these kind of net out, we end up taking 15 periods rather than 19 to exhaust. So at higher discount rates, we tend to exhaust the resource somewhat faster. Whereas if the discount rate is lower, say 5%, then the time period it takes, right, to exhaust the resource does extend a bit. Right, so we're going to have the rule that as the discount rate is lower, right, then the resource will tend to last longer. Now, all of this that we just did was assuming that the market for the resource is competitive. So we have lots of producers out there, right, for this particular resource, and they're all competing with each other. Right? And as a result, nobody really has much individual control over the price. Rather, it's you're having to face competition and then the constraints of demand. What happens, though, if we have a resource where the market is heavily monopolized, right? So we might have a resource like, say, oil, where 40% of the market or so is controlled by OPEC, right? Which, how well it does not being competitive kind of varies year to year, and that's going to be some of the complication we'll get to with the oil markets. But it doesn't feel like it would be as competitive, right? If we have almost half of the market being controlled by a single entity. As long as they're doing a good job of acting like a single entity, there's not going to be a whole lot of competition necessarily. Or similarly, you can look at aluminum. Right? Aluminum is another one. It's a highly concentrated market. Right? So what happens then if instead we look at monopolization? Right. Well, the previous example, assumed the price was the result of just supply and demand and competition. Right. So if we have a monopoly instead that owns the resources, that means the price isn't subject, right, to competitive forces anymore. Rather, the monopoly gets to decide what the price is. Now, they still are constrained by demand, though. Right. So say if we use the same demand curve as we did in the previous example, right, this monopoly can't charge over 50 units or people are just going to switch to an entirely different good. Right? So they are still constrained by how much people are willing to buy at various prices. But they are not constrained based on the prices that other providers of this good are charging. Right, so in order to account for this, we need to modify the hoteling rule slightly, and that is we'll use marginal revenue instead of price. And I'm not going to go into a lot of the details of marginal revenue here. You don't need to worry too much about that. But what you do need to know is that the price is a bit above marginal revenue for a monopoly. Right? So the consequences of this is going to be that at the beginning, the price will be higher if we have a monopoly. Right? We'll also see less of an increase in price over time, right? Because it's really the marginal revenue that is increasing at the discount rate. It turns out as that happens, the difference, right, between price and marginal revenue is going to decline. And resources, it turns out, are going to last longer if we have a monopoly that's in charge of this. And this all flows very naturally from the fact that they charge higher prices on average. If you charge a higher price, then people aren't going to want to buy as much of it in any one period, which means that the good lasts. Right, so in this case, if we have okay, let's point out some of the differences between this and the previous graph. Right, so here we have that same price and quantity over time. The first thing to note is that this good now lasts 30 periods before we exhaust it, so it's an additional roughly 50% in time. Right? The price, though, is significantly higher when you look at those beginning prices. Instead of being about, remember, it was $8.50, something like that. Now we're looking closer to $26, $27 as being the starting price, and that increases by 5% in each period rather than by 10% in each period as was previously the case. Right? Though again, it does have that trait where we will, when we exhaust the resource, our price is just barely underneath, right, that backstop price. Okay. So one more modification that we'll want to make to the hoteling rule, right, is looking at, well, what if we have a non-zero cost? Our previous examples, when we looked at both the original hoteling rule, which is just the price increasing by the rate of discount, or marginal revenue increasing by the rate of discount for a monopoly, those both assumed that it didn't cost anything, right, for us to get the resource. Like, we already had it. Effectively, we have just kind of this pile of resource available. We're trying to figure out how to divvy it up over time. But of course, in reality, if we're doing something like drilling for oil, some oil is relatively easy to get to, but still costs something to produce. Some oil is relatively difficult to get to, and certainly costs something to produce. Right? There is not a zero cost when you're trying to get, say, oil out of the ground, when we're trying to produce coal, or when we're trying to produce any of the metals, right? These types of things. Right, so if we want to account for the fact that it is actually costly for us to get these resources to start with, we need to replace price in the hoteling equation with marginal profit, which for a monopoly would be marginal revenue minus cost, or if we have a competitive marketplace, it would be price minus marginal cost. Right, so what this will then allow us to do is this marginal profit that is going to increase by the rate of discount over time. Now, for us to make any kind of prediction then about prices and quantities used, we need to know something about marginal cost and how that moves over time. Right, so remember, marginal cost is the cost of producing one more unit of a good. Right, so you can think of it as kind of the incremental cost. And this is really going to be a function, right, of the rate of extraction and the reserves remaining. Right, so first, if you have a higher extraction rate, right, so we're trying to remove, right, more of the resource than we previously would have, say. Right, what that's going to do is tend to increase your marginal cost. The reason being that we have some resource that is relatively easy to get to, some that's relatively difficult to get to. As I'm trying to extract more, right, then that incremental cost is going to increase because I'm having to use harder and harder to get to units of the good. I'm going to have to go deeper into the mine. I'm going to have to drill through less geologically easy areas to get oil out of the ground or natural gas out of the ground or what have you. So higher extraction rate will tend to increase your marginal cost. On the other hand, higher reserves remaining tends to decrease your marginal cost, and it's really the same reasoning. If we have lots of reserves remaining, odds are some of them are going to be relatively easy to get to. Whereas on the other hand, if we have relatively few reserves remaining, right, then it's going to be generally more difficult to get to them. Right. Now, the exact path of prices, though, is going to depend on how marginal cost changes over time. Because one thing that we know is that, okay, over time, we're going to change our extraction rate and the level of reserves is going to change. Those will have an impact on marginal cost. But it's also true that marginal cost changes for lots of other reasons. Right? It might be that we develop new technologies that allow us to extract resources in a more efficient manner, for example. This is something that we've seen basically in any form of resource extraction. We've gotten better at it over time, right? That is, the marginal cost has declined because of technological advancement. Now, it's offset somewhat by the decrease in the number of reserves available, but just to say, right, marginal cost is going to change over time in a way that is not entirely predictable. Nonetheless, right, here I'm going to run a model. In this case, I'm looking at, I assumed that my marginal cost was a rather simple function of 100 times the percentage of remaining reserves that we were extracting in any particular period. So the more we were extracting, so just kind of that quantity extraction going up, that increases the rate of extraction, which would drive up our marginal cost. A second thing that happens is that as you're increasing the rate of extraction, that means that the next period you'll have fewer reserves remaining, so that would drive up the marginal cost over time. And here we can see what happens, right? So the one thing, I modeled this out. Remember, I gave them a total of 50 periods. It turned out that they never actually totally exhausted the resource. Rather, they just kept extracting kind of a small portion of what was left, to the point where it was basically zero by the end of 43 out of the 50 periods I allowed. We can also see the path here, kind of an interesting smoothness to it, in that as we approach that backstop price, the price increases start to slow down, right? And also the quantity that we produce, right, starts to kind of level off as it's heading closer and closer to zero. Right, so this would suggest, right, that as we're getting to the point where we're going to run out of the resource, the reason for this is that the marginal cost goes way up, right, because there just isn't much of the resource left, and that's going to drive the marginal cost way up. That's going to tend to eat into our marginal profit unless we increase the price significantly. Right, so as the marginal profit is getting eaten into, right, then we are not able, right, to produce so much. Okay, or we wouldn't want to extract all of it, being the point. So now the question then comes, so we have all of these kind of nice predictions for the hoteling rule telling us how prices are going to move over time. So how good does it do? It turns out it's actually not a very good predictor. Even at kind of the most basic level of prices should go up over time by basically the rate of discount. Right? That doesn't even predict the overall trends that we see in most of the resources that we can track. But now, so why would this not be the case? Well, first, one of the key assumptions of the hoteling rule was that we have constant demand. Right? So even though the quantity that gets demanded is changing over time based on the price changes, that equation that I used, right? So that is that the quantity demanded is 50 minus the price. I assume that same equation applies in every single period. Right? So that same equation would apply in year 1 as in year 19. Right? But of course, this probably isn't true. Right? Demand does shift over time. Right? Say more people buy cars as, say, those middle-income countries develop more, or we say if people decide that they want to actually live closer to work, say, perhaps, right? So that can change demand as well, as we just kind of have these cultural changes where people either want to drive more or less, would be something very applicable to oil markets, as people shift from wanting to use more or less plastic, being another case. Right? So the demand shifts all over the place. Right? Another problem is that this all assumed either a constant marginal cost, whether it be going all the way back to zero, or being a constant marginal cost function, right? As we saw in just the most recent example, where that same ratio, 100 times the rate of extraction, right? So as a percentage of the remaining reserves, there's no reason that 100 has to stay 100. It could change over time. As technology improves, it would probably drop. We could also have regulations step in that can increase the cost of producing in a particular unit. Right? So the marginal cost is also going to shift over time. Right, so as that happens, that means that this price path is not going to end up really being smooth. Instead, it will end up much more jagged. And it also makes it significantly less predictable, as we're kind of jumping from one predictable path to another each time demand changes or the marginal cost changes. Right? Which means that on the whole, if we use kind of just standard supply and demand reasoning, that tends to do a lot better in terms of predicting what prices are going to do compared to something like the Hotelling rule. Now, if it were the case, right, that say demand shifts were just kind of temporary, right, so demand would shift one period but then tend to shift back the next. So in a sense, I would use the term wobble, right? So demand, it's not perfectly constant, but it kind of wobbles around a relatively stable average. Or the same thing with marginal cost, right? So if marginal cost, it's sometimes higher, sometimes lower, but it kind of wobbles around a stable average, then we'd still expect the Hotelling rule to work in the long term, just things wouldn't look as smooth, right? So we'd have a jagged line around the trend that Hotelling would predict. But the reality is that's not how demand and marginal cost work in these markets. Demand shifts are often basically permanent. They tend not to undo themselves. The same goes with marginal cost shifts, especially when they're driven by things like technological advance. We don't then forget these better techniques that we learn, right? So that ends up kind of undermining the ability of the Hotelling rule to have a whole lot of predictive ability. And we end up having to assume that basically the world's not changing, and it turns out that assumption is wildly inaccurate for these markets. So now let's turn to the issue of resource scarcity. So the basic question that people are often interested in is, are we running out of whatever the resource is, right? Are we going to run out of oil? Right? Have we hit peak oil is the phrase you'll sometimes see. Right? Are we running out of coal? Are we running out of aluminum? Are we running out of, take your pick. Right. Now this seems like a really basic question. Right? If we have some sense of how much is out there, we have some sense of how much we're using, right? We should be able to figure out, right, how much we have left, right, in kind of a practical perspective. But it turns out that this basic question isn't so basic for a couple reasons, right? So one being kind of the key is, well, what does it really mean, right, for a resource to run out? Right? After all, there's a difference between what we would call kind of the physical reserves, right? So if you look at all of planet Earth, right, how much iron is there? Right? That would be your physical reserve. But then there's also what we would call the economically viable reserves, or the economic reserves. Right? So those would be, say, the iron that we can actually get to in a way that is efficient for us. Right? So we have the technology to get to it. It's not outrageously expensive, right, for us to get to that iron. Right? So the economically viable reserves would be kind of those that we think we can actually use, given kind of the price that we have for the resource and the cost of producing it. Right? So this would create a complication of what do we mean by running out? Are we talking about physical reserves running out? Or are we talking about economically viable reserves running out? Right? And we would end up naturally with two vastly different answers, unless we just happen to be so good at producing a particular resource that all the physical reserves are actually economical for us to use. Right? But I don't think there is actually any case where that is true. Right? So when we look at resource extraction over time, right, and this is important in thinking about this question of running out, there are really four relevant factors, right, that will affect our resource extraction decisions. The first is the minimum marginal cost and also the maximum marginal cost. Right, so the reality is that when we look at any particular resource, right, there's actually an entire range of marginal costs that we face depending on the specific reserves that we're trying to tap into. For example, one of the big things, like why the Middle East is so powerful in the oil market, is that their oil is relatively easy to get to. Right, so they actually have a fairly low marginal cost. Whereas if you look at, say, the oil shale fields, we tend to be relatively worse at getting the oil out of oil shale. Right? So it turns out the marginal cost there is much higher. Right? So we have kind of this range of marginal costs that will actually exist at any particular point in time in the market, and both of these these two boundaries, the minimum and the maximum, tend to change over time. right? So one is that, on the one hand, the minimum marginal cost tends to rise over time. This is perhaps offset a bit by changes in technology, but the reason here is fairly straightforward, in that if you're using the easiest to get to reserves first, then you're not going to have them, right, in the next year, right, or the year after that. Right. So as you're using up the easiest to get to resources, that means your minimum marginal cost is going to tend to rise as you're having to use more and more difficult to get to resources. Right. On the other hand, the maximum marginal cost is going to tend to drop over time, right, as we tend to get better at exploiting these resources and getting them out of the environment where we can use them. Right, so we'll tend to find this convergence in marginal costs over time, the minimum rising, the maximum falling. The price, as we've already shown, according to the Hotelling rule, will tend to rise over time. Right? So this is very much assuming other things equal, knowing what we know about the general trend of marginal cost, right, we would expect the price is going to rise over time. Okay. The backstop price, though, kind of that maximum that people are willing to pay for the good, is going to tend to drop over time. The reason here is because, again, of technological advancement, right? So as we advance in technology, that not only, right, makes us better at getting at kind of those hardest to get to oil reserves, for example, it also makes us better at producing whatever the alternatives are, right? So I don't know, hydrogen fuel cells or what have you. So this is going to tend to push the backstop price down over time. And so as we approach exhaustion, what we would expect to happen is that all four of these are going to tend to converge. Right? As we're running out of the resource, the minimum and the maximum marginal costs come together because we don't have a whole lot of reserves left, and they'll tend to be very similar to each other. Right? The price is going to also tend to converge there as it's heading toward our backstop price, right? Which we know that would tend to happen over time, and the backstop price falling, and we're all kind of moving toward that one point. Right, so this is kind of a fact that some people may try to use in order to try to figure out, right, whether we are exhausting a resource or not. Different ways we can measure resource scarcity to get at this question of how close are we to exhaustion. So there are four different ways that we can use this. Each of them kind of has its own strengths and weaknesses as far as that goes. Right? So there's the resource lifetime, which I think is probably in the popular press the most common that you would find. We have the unit cost, real prices, and also economic rents. Okay. So let's go through each of these in turn. Right, so the typical approach for the resource lifetime is that we take those economic reserves, so those reserves that we can actually practically get to and use in a cost-efficient manner, and we divide that by the current annual consumption. Right? That would then tell us, right, how many years we have left. Right? So if we know how much aluminum is available to us, we know how much we use in any given year, we do the division, find out, oh, well, we have 1,000 years of aluminum left, which is fairly close to some of the suggestions for aluminum. Okay, so we have quite a bit of aluminum left. On the other hand, it looks like we're running out of something else. I don't know, right? Oil, right? Or lead. Okay. Right, just take those reserves, divide by current annual consumption. We have 17 years of this, we have 1,000 years of that, and so on. Now, it turns out, though, that even this basic approach, it's not obvious this is the one we should use. Right? After all, the economic reserves, that's going to be affected by our advance in technology. So it might be that it makes more sense and will be more accurate to use physical reserves instead. Right, so instead of using economic reserves, use physical reserves, and then we find out that we have a whole lot more of this resource than we thought. Right? Because if we assume that we can eventually get to all of it, then we can use a whole lot more, right? At least most of the time. Right? Another problem would be, well, annual consumption we know changes over time. After all, the population is growing. Right? We would expect as we have more people, we would consume more of most resources. So it might be that we want to change that. So another thing we'll sometimes see people do is change the current annual consumption and instead, right, develop a growth path for that. Right, so then you would track over time, right, the reserves available and then how much annual consumption you have in that year as a projection, and then you would kind of go through and calculate where is it that you run out. Okay. Right, so this is a fairly straightforward approach as long as we have a good measure of economic reserves and current annual consumption, or these other measures that we could possibly use. Right, we can run a few different versions of this fairly easily. The math isn't that difficult. However, it turns out there are some significant issues with using this particular approach. One is that it ignores the possibility of innovation, right? Except for using all of the physical reserves, then we're assuming innovation becomes absolutely perfect and is basically unlimited, right? So either side, we're ignoring, right, how innovation actually works and that we do get better. So what our current economic reserves will tend to grow over time, but we tend not to get perfect, right? So using physical reserves in place is probably not going to be true either. Another thing that this does is it ignores the fact that we tend to substitute away to other resources. Right? So if we think about the hoteling rule, it claims that these resources will tend to become more expensive over time, and this is something, even if we accept that the hoteling rule is in itself not true, right? If we acknowledge that resources become more scarce over time as we use them up, right, we would expect prices are going to go up. Right? Well, as prices go up, then we're going to start switching away and using other resources, right, that don't have as many problems with that. Right, so it turns out this is totally ignored when we do this simple calculation. We assume this current annual consumption is going to last forever, right, or that it's going to grow at some fixed rate forever until we run out of the resource. Where, of course, the reality is that the closer we get to running out of the resource, the more expensive it will become, and therefore the more likely we are to substitute away to other resources. So this also ties in a third issue, that is ignoring any price effects, that as we start to run out of a resource, we'd expect the price to increase, right, which would further lead to us substituting away into other resources. Right, so current annual consumption we'd expect will actually fall if we get really close to using up all of a particular set of reserves. Right, so this is going to be inaccurate. It will either vastly overestimate or vastly underestimate, and it's not always easy to tell which direction it's going to go. Right? This is kind of a fun fact, and that some economists have found that when you look at people's projections for what lifetime, kind of the resource lifetime is for any particular resource, it tends to be constant over time. Right? So if you go back and you look, say, in 1970, they'll say, oh, we have 70 years of oil remaining. And then you come forward to today, 50 years later, right? Sensibly, we should have 20 years of oil remaining at this point. Right? Instead, we have 70 years of oil remaining. Right? This is just an example. I don't know how much it actually is for oil. I mean, sensibly, like logically, if the resource lifetime approach was at all accurate, we would expect that the resource lifetime should fall by 1 year each year, right? So like if you ask me how much of my life I have remaining, right, when I'm first born, I'll say, well, I won't say this myself, but we think in terms of, well, life expectancy is about 78 years. So when I'm a newborn, I have about 78 years left to live, right? On the other hand, if I'm 40 years old, well, I have about 38 years left to live. If I'm 70 years old, well, I probably have about 8 years left to live, right? That type of thing, right? We shouldn't say year after year, oh, I still have another 78 years to go, right? So logically, it should decrease 1 year by each year. Instead, it tends to be roughly constant. Right. So what that suggests, right, is that our rate of technological improvement or innovation seems to be just enough, right, for us to make just a few more resources economically viable, and it's at the same rate as which we're using them up. Right. Or, alternatively, if we can't find those innovations, we tend to decrease our annual consumption, right, in order to make sure that we have enough available resources going into the future. Right. So it seems to suggest, if resource lifetimes are constant over time, that our resource producers, right, have this desire to make sure that they have, right, some set of lifetime, right, in the resources that they're trying to exploit. Right? So they want to make sure that they keep 70 years worth of this resource available. And that means either, right, that they are going to innovate, right, or that they're going to cut back on production. Right? So it looks like what we actually see is that resource producers seem to be managing around the resource lifetime, right, which is kind of an interesting thing. Okay. But that also means that it's a very poor predictor. A second way of looking at resource scarcity is based on unit cost measures. Right, so the basic idea is that as a resource becomes more scarce, it becomes more expensive to produce a unit of it. Right, so this would capture that idea that the minimum marginal cost is increasing over time. Now, technically, unit cost measures are not based on marginal cost, they're based on average cost, but it nonetheless is trying to get at that same idea, that as we start to run out of a resource, it becomes more difficult to produce, right? So we have to pour more resources, labor, capital, into producing an additional unit of it. Now, when we look at the evidence regarding unit cost measures, it appears that unit costs are dropping over time for most resources. Right, so that suggests that we're not using up resources. Instead, resources are becoming more abundant over time, which is kind of interesting. Right, so this would suggest then, right, innovation is actually increasing the economic reserves faster than we're using them up. Right. Now here, an important point is that unit costs we calculate as being the cost of labor plus the cost of capital. Right. So this would include, right, the workers and all of the machinery that we're using in order to produce these resources. However, we want to be a little bit cautious about this because this feels very optimistic. A couple things to keep in mind. Right? So first, this does rely on the assumption that we are pursuing the low-cost reserves first, where in reality we might not actually know, right, which reserves are low cost. Right? So it might be that we see a drop in unit cost just because we happen to be getting lucky and in our exploration, oh wow, we just found a new source of this that turns out is really easy for us to exploit. We didn't know this resource existed here before. Right? So this is sometimes called the Mayflower problem, where it's been observed, right, that if the Pilgrims, they came over to America, right, they landed there at Plymouth, and they set up their settlement, and it turns out that New England is a terrible place to farm. Right? Nonetheless, right, they farmed there for a really long time before finally agriculture tended to move more toward the Midwest, where we have much more fertile soil. We're much better at producing agricultural goods in the Midwest than in New England. Right? So the issue here was that the Pilgrims just didn't know, right, where the best place was if they were going to start farms. Right? Instead, you just kind of use the resources you have available that you know about. And that is exactly the same problem here, is that if we already know about a particular set of resources, we're going to use the ones we know about first, and then it might be that further exploration will lead to a decrease in the cost of our reserves. And it's not because we aren't running out, it's just because we happened to find the easier to use resources later. A second caution would be that using just capital plus labor is actually missing some other significant inputs. Most important here would be something like energy. Right, so it might be that what's actually happening is that we're using less capital, using less labor in order to extract resources, but we're offsetting this by increasing the amount of energy that we're using to extract resources. And it turns out if you look at some resources, it's very clear that capital plus labor, those costs are falling over time. But once you throw in energy costs, then we see that capital, labor, and energy all added together, those costs have actually increased slightly over time, which would suggest that resources are becoming more scarce. Another issue with this is that it doesn't really have a forward-looking component to it, right? So it's not really thinking about what's going to happen in the future. You can't predict that. Rather, we're just tracking what happened in the past, right? So we are comparing unit costs now with unit costs last year or last decade or 50 years ago, right? So this does allow us to tell how we're moving, but doesn't really predict how we're going to move in the future. Another measure would be real prices. Right, so real prices, that is, when we take the price of a good but adjust it for average inflation, they could be a measure of scarcity, and this is true of most goods. Right? So this is not just for resources like natural resources or non-renewable resources even. Right? So with any good, if we have an increase in its supply relative to the demand, either because the supply is increasing rapidly, right, faster than demand is increasing, or perhaps because demand is decreasing rapidly, in any case, if supply is growing relative to the amount of demand, prices are going to fall over time. Right? So as a good becomes less scarce, right, more available relative to the demands placed on it, prices will fall. Right? On the other hand, if we have an increase in demand relative to supply, then prices will tend to rise over time. Right? So it's fairly clear just from basic supply and demand, right? Prices tell us something about the relative scarcity of goods and how they're changing over time. Well, if you look at real prices, that is prices after we adjust for inflation, this seems to show something of a U shape for most resources, with prices rising since about the 1960s for many. Now, there are some exceptions. So, for example, if you look at coal and copper, we see relatively clear rises in their prices from the 1960s forward. But if you look at, say, aluminum and iron, then it's not so clear that there is any trend. It appears to be somewhat flat. Right? So the flatness of real prices would suggest, actually this goes back to the idea of resource lifetimes being basically constant over time, right? That we're kind of managing the supply in such a way that it's not like we're running out. We're not really getting more abundant either with these particular resources. We're kind of managing the supply to meet demands relatively, I guess I would say, well. Okay? We're keeping them in balance. However, there are problems with trying to use this measure. One is that it ignores the effects from things like cartels. Right? Cartels are interesting. So when we look at things like OPEC, for example, right, and that their prices might vary, not because of kind of these underlying supply and demand forces, the cost of producing and then the demands that people have for the good, but rather just based on our ability to coordinate. Right? So when we have a cartel, we're kind of torn in two directions at the same time, and we can explain this using game theory. Right? So on the one hand, right, when we have a cartel, if we all act together and cooperate, right, we end up acting kind of like a monopoly. Right? And a monopoly is going to be able to charge high prices because it's restricting the quantity of the good available. And so prices are going to go up. Right? On the other hand, there is an incentive for each member of the cartel to cheat on these agreements, produce a little bit more. If they produce a little bit more, then that drives prices down. Right? So then there's this incentive when you look at kind of the overall effects that everybody's just going to cheat on the agreements we make. Right? That's going to drive prices way down. So what does that mean then? It means that prices, if we have a market where there are cartels, and the cartels aren't perfect, right? Sometimes they work well, sometimes they don't, then what these price changes might be capturing is how well our cartels are coordinating. Right? So when the cartel is all getting along very well and they're cooperating very well, prices go up because they're acting like a monopoly. On the other hand, when they're not coordinating very well, when they're not getting along, then they start engaging in price wars, start producing more, and prices start falling. And it's not because the good is more available in any kind of fundamental way. Right? It's just that the cartel has fallen apart. Now that does make the good somewhat more available, but not necessarily in any kind of long-term way. Right? Rather, we're just capturing the effects of kind of these short-term changes in the relationships of members of the cartel. A second thing to keep in mind is that government intervention will sometimes distort prices. This is often if we have, say, government-run resource providers, which we tend not to have so much here in the United States, but in many countries you do actually have that, where the government will own an oil company. Right? And this is just something that you will see governments do. So not unlike, say, in the United States, governments will often run things like the water supply or sewers, that kind of thing. You will often see that with just base resource producers in other countries. Right? So then what government will sometimes do is they'll distort prices of those goods that might be competing, right, with the goods the government themselves are trying to use. Right? So it might be that the government has put in place, right, a price floor, right, so a minimum price on a good that they would directly compete with themselves. So this would effectively be equivalent to letting Chevy decide what the price of Ford was going to be, right? So they decided, oh yes, well Ford's, you definitely have to pay a lot for them, right? And then suddenly Chevy looks a lot better. This is effectively the same thing, right? Government, in order to advantage their own production, decides to force the prices of other goods higher. And this distortion of prices then means that they're not actually reflecting supply and demand anymore, right? Instead, they're just reflecting government intervention. And so real prices will tend to miss that particular fact, or will be affected by that fact. Okay. Another thing that this is sometimes criticized for is that it misses any of the environmental impacts from extraction, so any of the externalities that happen. Right? So the real price doesn't necessarily capture the fact that with a lot of extraction processes, we're actually doing damage, right, to the environment. Now, I would say that well, while I think that may be true in a sense, in my mind, this doesn't change the ability of real prices to tell us something about resource scarcity. Right? So I think that this particular criticism is not quite as relevant to the question of whether this is a good measure for resource scarcity or not. Whereas the first two, right, the problem with cartels and the problem of government intervention, those do actually make it difficult to use real prices as a way of determining whether a resource is becoming more or less scarce over time. Okay, and the fourth way that we can try to measure resource scarcity is based on economic rents. So economic rent is defined just as the price minus the marginal cost. It's not quite the same thing as profit, right? So profit would be based on price minus the average cost. The marginal cost is usually a bit higher than average cost, right? So it's not quite the same, though they will kind of move together generally, but not always. Right, so the basic idea here is that if we have rising rents, that's a sign of increasing scarcity. Right? If we have an increase in scarcity, right, then you can charge a higher price relative to your cost for any particular good. And so that's kind of the basic idea here. Right, now there are a number of problems with this. One is that we have a lack of data. It turns out that calculating economic rent is just not an easy thing to do, because while prices are observable, marginal cost is not. Right? It turns out that even producers might not know exactly what their marginal costs are. Right? Now, they will often have a better idea than I as an outsider would, but they may not know exactly. Right? So even if I thought that they were going to be honest with me and I asked them, what's your marginal cost, what's your incremental cost, I suspect that a number of producers just wouldn't know. Right? They'd have to kind of do the math and often don't find it worthwhile to do it. Rather, they're making decisions as best they can in accordance with what they think makes sense. Right? And explicit marginal cost calculations aren't always a part of that. Okay. Right, so having a lack of marginal cost data means that we then can't calculate economic rents at all. It's just not observable. A second problem with using economic rent is that this statement about rising rents being a sign of increasing scarcity assumes that firms are following an optimal depletion plan. Right? Where in reality, right, they don't have good information about future costs or about future prices. Right? Because of that lack of good information, they might not be following an optimal depletion plan. Right? They don't know what the optimal depletion plan actually is. Right? Instead, they're doing the best they can with projections for costs and for prices, but they don't actually know what the future holds any more than anybody else does. When I think about future costs in particular, I think of the role that innovation plays. Right? Like the reality is that if we know what innovation is coming, right, then we already have it. Right? The whole point of an innovation is that it's a new idea, right, that can then improve things. Right? If we know what the new idea is going to be, then we must already have that new idea. Is kind of the idea here. Right? So you can't actually predict what the effect of innovation is going to be just by the nature of what innovation is and how it works. Right? Right, so having good, clear, accurate predictions for what costs are going to do over time or for what prices are going to do over time, we know is just fairly unlikely. Okay. A third problem is that interest rates will affect the optimal plans. Right? So even if we don't have a problem with information about future costs and prices, then interest rates are going to create issues. Because go way back to the hoteling rule, right? We showed that if we change discount rates, which are very connected with interest rates, then that changes, right, how long you should take to deplete a resource. Right? Higher interest rates, higher discount rates, you want to use resources up a bit faster. Lower those discount rates, you want to use them up a bit more slowly. Right? And what that means then is that as interest rates change, right, the price path that is optimal will change. It's not just the price, this period while interest rates are different, but the entire path changes based on how interest rates move. Right? So it turns out then that interest rates have an effect on rents without necessarily changing scarcity at all. Right? So it turns out economic rents would not necessarily be a good measure even if we could get the data for them. Now, it may be somewhat frustrating at this point, as we've gone through all 4 different ways, right, to measure resource scarcity and have concluded that all of them are flawed. Right? Well, sometimes that's the reality. There are some things that are just extremely difficult to measure with any kind of precision. Right? So often what we have to do is just do the best we can. Right? Go ahead, right, calculate what the resource lifetime is, but keep in mind the weaknesses of that approach. Go ahead and check the unit costs, but keep in mind the weaknesses of that approach. Go ahead and check the real prices and what they're doing, but again, keep in mind the weaknesses of that approach. I'm one that believes that if you use all of those 3 approaches that we know we can get fairly good data for, right, then we can start comparing and getting more of a complete story. Right? So what is the story that one of them tells us? What's the story that another tells us? Are they telling the same story or not? If they're telling the same story, then we might want to tend to believe that these weaknesses that we've pointed out may not be so severe. Right? On the other hand, if they're telling different stories, then we need to figure out kind of which one is having the greater weaknesses at any particular point in time. Now let's turn to looking at oil as a case study. So first I just want to share with you some of the data, and then we'll make some comments about it. Right, so this is showing oil prices over time. I got data going back, as you can see, into about the mid-1940s. Now I will say I don't totally trust the data before about 1980 or so. This just feels a little bit strangely stable to me. But nonetheless, this is the data that we have available through FRED, that's Federal Reserve Economic Data. They have a wealth of information available, and so it certainly would suggest if you have questions on what economic data looks like, going to FRED is kind of the first place that I would try, because they gather from a bunch of different sources, right? So here you can see this information originally came from the U.S. Energy Information Administration. Right, but then the Federal Reserve is the Federal Reserve Bank of St. Louis, which you can see on the slide, is the one that kind of compiles all of this and offers it available for free through their website. Right, so I just want you to take a look at this. Now, one issue with this particular graph is that it has not accounted for the effects of inflation. Right, so part of the reason that oil was so much cheaper in 1946 than it is if we come forward is just because prices in general have risen. Right, so what we would need to do then is to adjust for this. And that is what this graph has done. This graph is showing what we would call real oil prices. That is, we have adjusted them for inflation. So this is showing kind of how that path goes over time. I wouldn't put a whole lot of weight in the exact numbers on the vertical axis, but rather focus on the movements and the changes. Right? So we find that once we adjust for inflation, the price of oil, when you look at, say, the late 1990s, there we had kind of a little trough around, that's 1998 or so, was about the same as the prices that we saw when you look before 1975. Okay. Right, we can also see a number of other things here. So let's go ahead and get to some of the comments about this. So just take a look at this, absorb it, and then we'll move on. So a couple of comments about what oil prices have done. The first thing that we would observe is that there's a lot of volatility, right? So once we get past about that 1980 point or so, when I think the data gets a little bit better in terms of its quality, we see jags all over the place. It's very jagged. It's nothing like those very smooth paths that we saw in the previous example about the hoteling rule. Now, there might possibly be some weak upward trend, but we notice it's not really one that we can rely on happening. In fact, for long periods of time, when you go from very early in the data set to about 1970, 1975 or so, we saw a very weak downward trend in prices. And then we managed, right after we had some increase, we had a decrease right back to about those levels, right? And then we have another increase. It's not so obvious how much of an upward trend there is here, or if there even is one. But there might possibly be, if there is a trend, it's weakly upward over time. Right? So the question then would be, what describes prices? Right? Because it looks like Hotelling's rule, which would suggest that we should have a clear upward trend, is not working very well. Right? Well, it turns out supply and demand do a fairly good job. Right? Now, why is it then right, that we'd have prices going all over the place? After all, isn't the supply of oil something that is fairly constant? And it's not jagging all over the place, certainly. And we know that the demand for things like gasoline or plastic products and so on, that this is not something that jumps up and down in any kind of significant way. I think probably the most significant change we've had in demand has been recently, as we have all of these stay-at-home and shelter-in-place orders around not just the United States, but much of the world. Right? Okay, that's probably leading to a significant change in something like the demand for gasoline. Right? But apart from like the past month or so, or here we are, say in early April of 2020, apart from, say, this weird coronavirus effect on demand, we wouldn't expect demand to jump around nearly as much as it seems like it does right from the graph. Right, so what is happening there? Well, it turns out that elasticity plays a significant role. Right, so what elasticity is, it's a measure of how much people respond to price changes. Right? So one thing that happens, right, is that if you have demand or supply that we call inelastic, what that means is that a small price change has almost no effect on people's willingness to buy the good. Right? And this is the way we would typically expect that something like the demand for gasoline would work. Right? If you increase the price of gasoline, I know I've seen it anywhere between, in my lifetime, I've seen 99 cents and I have seen $4. Right? And I suspect people aren't driving significantly less when gas prices are $4 a gallon than when they were 99 cents a gallon. Right? Or even like within the past few years, I've seen between $2.50 per gallon, not being unusual, to more recently, right before we shut everything down where I live, I was seeing prices around $1.70 a gallon. So this is an enormous difference in prices when you think about it. Right? One of them is 50% higher than the other, more or less. Right? And yet, right, I don't change how much I drive. Not in any significant way. I still drive to work basically the same amount. I still drive and do errands about the same amount. Right? So this would be a sign that demand is relatively inelastic. That is, these big changes in prices don't really change how much I am willing to buy. Right? And it turns out the same is true on the supply side. The big changes in prices don't seem to have a big effect on how much oil is produced by oil producers. So whenever we have a market like this, where quantities are relatively stable, people don't respond to prices very much, then it's much more likely you see prices that are extremely volatile. And so prices, like if there is even a small change in supply, for example, say that it becomes just a little bit more difficult to provide gasoline than it used to be, right? Well, in that case, we have a little bit less gasoline available. Right. So to convince people not to buy as much as before, prices have to go up substantially, right, to get people to change their behavior. Right. So that's why we get these huge changes in prices. Right. Similarly, if gas becomes more available than before, right, then we have to lower prices significantly to convince people to actually travel more than they otherwise would. Right. So it turns out that when you have this inelastic supply and inelastic demand, right, the quantity isn't changing much, but prices have to change a lot, because anytime there's even a small change in either supply or demand, it requires an enormous price change to convince people to change their behavior enough, right, to adjust to that change. Right, so part of the way we can explain the fact that oil prices are kind of all over the place, it's that the supply and the demand for them are very inelastic. Right? So people just seem not to be very price sensitive when they're making the decision to either produce oil or to buy and use it. Now I do want to take a little bit of time to talk about what has happened in oil markets here in early 2020, which is the time that I'm recording this. Because I think it's actually been something really interesting to watch from an economics perspective, and that we've recently seen an enormous decrease in the price of, I see it myself in the price of gasoline, but it's also fundamentally in the price of oil as well. Right? And what has happened is that specifically the Saudi Arabian oil company Aramco, which is what the royal family operates, and Russian oil producers have been engaged in what economists would call Bertrand competition, which is a type of competition that you find whenever you have an oligopoly, so relatively few producers involved, right, where they might want to form a cartel normally, but they're competing with each other on the basis of price, right? So they're effectively trying to undercut each other and start a price war. Right? And one of the predictions that we make is that if we have this cartel or this oligopoly and they're operating on the basis of quantity, right, then they're going to have this incentive, right, to try to form a cartel, and even if they don't form a cartel, they're still going to restrict production somewhat, right, in order to keep prices relatively high. And that's what we call Cournot competition, is when they're strategizing on the basis of quantities. But once they switch over to Bertrand competition, both of these models come from the 1800s, and Bertrand was specifically responding to Cournot in kind of describing the way this kind of competition works. Right? And what Bertrand suggested is that if instead of focusing on quantity, we have our producers focus on price, then they have a strong incentive to always just kind of keep undercutting each other until they get down to the point where they're losing enough money that they decide it's not worth it, right, to cut any further, right? So, and that is exactly what it seems we have been seeing. When you look at the statements that are often made by, for example, OPEC will often announce based on production numbers. Say, oh, we've decided to increase production by 10%, or we're decreasing production by 5%, or what have you, right? So it uses this Cournot kind of language. It's all about quantity that is being produced. But more recently, what we've seen is that statements coming from oil producers have been much more related to prices and what the prices they're going to charge, right? So this change in terms of kind of what they're strategizing around, right, has created this change in the dynamics of the market, so that now we're observing more Bertrand competition, and it's effectively a price war. So this is a case where, again, this can be explained through supply and demand. It's just that we now have suppliers that, if you're charging slightly less, you need to provide a little bit more, right, to the market, because people want to buy a somewhat more. Right? And that is exactly what has happened here, is that because we have these firms targeting pricing, right, they're each increasing the supply available, and that's driving prices further and further down according to the targets they're making. And the target prices that they want to make is always going to be just slightly less than the other guy. Right? So we see this leapfrog sort of effect where Saudi Aramco is going to charge a slightly lower price than Russia previously did. Right? Russia then decreases its price below what Saudi Aramco did, and we have, right, this effect where it'll just keep dropping until both of these firms find that it's worthwhile to stop the process just because they're losing too much money. And so this would be an example where you notice all of the logic here does not seem to be much about the hoteling rule, right, and the decision about, right, should we produce now or should we produce in the future. Right? Rather, it's being captured by other economic theories like supply and demand and game theory. And so I just thought this was something that was certainly worth talking about, because even before we take into account all of the effects from the coronavirus and what that has done, which has been significant as well, right? We saw this tumble in the price of oil really just on the basis of Bertrand competition, right? Which again is calling into question how useful something like the hoteling rule actually is for these types of markets.